So carrying on from yesterday, don't shout something, you don't need to do that. A inverse equals I. So we're going to try and calculate our A inverse to this generalised A form here. And to do that, I'm going to start by writing my A, B, C, D. And then I'm going to fill that in a minute. And then we also have 1, 0, 0, 1, which is our identity we're trying to get to. And inside here, I'm going to just say, let A inverse, for lack of something more original, be, actually let's start it with W, X, Y, and Z. So we'll just use the first 4 letters and the last 4 letters of the alphabet. South, no, good, okay. So we've got W, X, Y, and Z. And so now carrying out that multiplication so that we can solve it simultaneously. Remember, we've got 8 unknowns here, so we can't actually solve this, but we can solve for W, X, Y, and Z to get the values of those in terms of A, B, C, and D, and that will generalise our inverse. So this will become AW plus BY, and then AX plus BZ, and then CW plus CY, and then CX plus CZ. That's our multiplication, and that's equal to 1, 0, 0, 1, which in turn will give us the 4 equations, the 4 relationships. AW plus BY is equal to 1.
Where's D? CW plus CY?
Oh, sorry, D. Yeah, you're right. D should be here and here, shouldn't it? How's that? Cool, thank you. AW plus BY equals 1. AX plus BZ equals 0. And CW plus DY equals 0. And CX plus DZ equals 1. So there's our 4 equations. I'll give them names. 1, 2, 3, and 4. So there's our labels, so I can refer to them. But you'll notice here that as I'm building or trying to build towards a solution, this is quite a handful to solve for these. I eventually want to get down to X equals, Y equals, Z equals, W equals in terms of A, B, C, and D. But I can see that X and Z exist here and here. So I've actually just got a pair of simultaneous equations for X and Z and a pair of simultaneous equations for W and Y. So whilst it looks bad, it's not actually that bad. I'm dealing with 2 separate pairs. And so I'm going to run through and do those 2 separate pairs individually now. So we'll call this pair number 1, and that will be the, I'll do the W-Y pair. So we have AW plus BY equals 1. And if I rearrange this, hopefully you can see that W is equal to 1 minus BY over A. So that's my W, and that's the first equation, which is still equation number 1. And equation number 3 is CW plus DY is equal to 0. I can put my W into there now, which gives me C times 1 minus BY over A plus DY equals 0. So this is, I've subbed into equation number 3. And if I rearrange this, I want to solve for y. So what I'm going to do is I'm going to multiply by a, because that's a fraction and I don't really want fractions. And then I'm going to bring all the terms with y in them on one side and all the terms without y onto the other side. And I'll expand these brackets, so I get c minus bcy plus ADY equals 0. And that means that c is equal to bcy minus ADY, which means that c is equal to y times bc minus AD, which in turn means that y is equal to c over bc minus AD. How's that look to everyone? Good. Cool. So we've got our y value. And we can get our w value in the same way, and it's a bit easier because we've already got our w here. So w is equal to 1 minus b times y, which is c over bc minus AD, and then it's all divided by a. which is a bit of a pain to simplify, but I can write that down as 1 over A minus B over A times by C over BC minus AD. How's this going to work out? BC, let's see. I have faith it's going to work out. Just keep an eye on me and make sure I don't make any mistakes. I get BC minus AD over A times BC minus AD minus BC over A times BC minus AD. So what I've done here is I've just taken that first fraction. I want to bring the fractions together. So it's already got an A, but it doesn't have this factor. So I've multiplied by this factor, but I multiplied the top by that factor as well. This I've left the same, I've just combined it together. So now I've got the same denominator, and I get BC minus AD minus BC all over A, BC minus AD. And of course that's nice because the BC's cancel out. I get negative AD over A, BC minus AD, which of course gives me, I might just, which of course gives me negative D over BC minus AD. So that's my W value, and there's my Y value. Now, let's fast forward a little bit, because you've seen this now, and I don't want to bore you too much. So I'm going to fast forward a little bit and say if we do the same thing, we'll get something like this. X will be equal to B over BC minus AD, and Z will be equal to negative A over BC minus AD. That's what's going to come. That's what's going to come out of my method for solving these simultaneous equations. There's lots of ways you can go about it, but that's what's going to come out of mine. Yeah. It is, and I haven't gotten there yet. You've got to give me a chance. Is that all right? Okay, so this is a perfectly good generalisation. And what I was just saying is that's what's going to come out of my solution to the simultaneous equation. This is the natural place to stop, particularly with this C over BC minus AD. But definitionally, this is what's come about. We've got a slight change to the representation in that the D and the A are positive and the C and the B are treated negative, and the denominator, that's the word I'm looking for, the denominator is swapped. So I'll show you what I mean. Definitionally, what you have in the textbook and how we define the determinant, we actually have Y equals negative C over AD minus BC. So that's been swapped. So that's just what naturally came out of my solution there, but it has been swapped, and there's some good reasons why it is swapped, because it helps with the stuff later on. But W becomes, instead of negative A, it becomes A over BC minus AD, and X becomes negative B over, that's not BC, sorry, that's AD minus BC, AD minus BC, and Z equals A, that shouldn't be A either, should it? W, W's D. A over AD minus BC, which gives us this resultant matrix. A inverse, the thing we're trying to find, is equal to WX, Y and Z, so it's equal to A over AD minus BC. X is negative B over AD minus BC, and Y is negative C over AD minus BC, and Z is A, so that should be D, A over AD minus BC, and this is written in a more formal way and a simpler way by taking out the common factor, the scalar 1 over AD minus BC, outside of D, negative B, negative C, and A. So that's the standard form of our inverse. For any matrix A, B, C, D, this is true. So interestingly, we do get this common thing that comes out. That's just worked out algebraically. So what we now have is a situation where we can define things. I'm just going to move some stuff down while I'm talking. We can define certain parts and use them in our generalizations. So we get this thing here. That is called our determinant. So determinant equals AD minus BC. And that will be really important. So you'll be asked in this exercise and the two exercises that are quoted, you'll be asked to find your determinant, your inverse, and maybe talk about the identity matrices. The determinant is really important because it helps you to find the inverse. But it does one other thing as well. Some matrices are not invertible. What is it in here that would make our matrix not invertible?
Determinant is 0.
If the determinant is 0, because what does that cause?
A null matrix, whatever it's called.
It causes something in that matrix there. If the,
You can't divide by 0.
we end up with a divide by 0 error. So we also get, if the determinant equals 0, then A is not invertible. So what you'll have, like the exercise is probably going to be pretty much straight down the line. You'll do the exercise. Most of the questions are going to be invertible because it's not a very good question if it's not. But in your Term 3 exam, I'm giving you a trial external exam. It's going to be like the external exam will be, which means it will have 20 multiple choice questions. A really, really common multiple choice question would be, here's matrix A, is it invertible? Or something along those lines. And you will just be testing the determinant. You don't have to go through any process except just go that times that, bam. You'll notice also, you need to know this, those two have swapped, those two haven't swapped, but they're now negative. So you swap the leading diagonal and you negate the other diagonal. Yeah.
Will the multiple choice questions be ranked like complex unfamiliar?
No, not really. They'll be mostly simple familiar.
Why was it made negative from what you simplified?
Why was it? It's not like something that was deliberately done. What do you mean, from what I had?
Yeah.
The main reason is, when you get into some context, this, like I've just mentioned, that's the leading diagonal. And so it works nicely to have that leading diagonal as the leading term in the determinant for some particular context. It doesn't really change anything, but it more naturally works there. When you get to 3 by 3 determinants, and remember 3 by 3 you can do on your calculator, but in that next exercise it shows you the determinant for 3 by 3. The leading diagonals being positive means that the determinant for 3 by 3 starts with a positive term and only has one negative term instead of two. It just makes things slightly simpler. So, yeah, I mean, I guess, I don't know where the first person came to. That's where I've just naturally come to here. But had I have solved for, I think if I had have solved for W first instead of Y, I would have come the other way around.
Yeah.
The point is it doesn't really matter. But, yeah, it's pretty much irrelevant. This is just a generalisation. So a couple of examples. I'm actually going to break this up. Oh, no, I might break it up later. So I'm going to break it up at 13 minutes. So example 2, use your generalisation to find A inverse for A equals that. So I'm going to give you a minute to do that. See how you go.